Hello, my dear students. Welcome to IKSR chemistry classes. Here we are in lecture number 11 on the chapter Symmetry and Group Theory. In this video, we will discuss general rules for multiplication of symmetry operations. Some conclusions or generalizations can be drawn from the previous discussions regarding the multiplication of symmetry operations. We have already discussed the multiplication table for C2V point group and C3V point group, and from these multiplication tables we can draw some conclusions, and the first one is given here: the product of two proper rotation symmetry operations. The product of two proper rotation symmetry operations must be another proper rotation operation. It means the product of two proper rotation symmetry operations is always another proper rotation symmetry operation. An example is given here: C3 multiplied by C3 is equal to C32, that is C3 inverse. These two are proper rotation symmetry operations and their product is another proper rotation symmetry operation. However, proper rotation symmetry operation can also be generated by combining two reflection operations. Please note that the product of two proper rotation symmetry operations is always a proper rotation symmetry operation. However, proper rotation symmetry operation can also be generated by combining two reflection operations. Let us see it with example. Sigma xz into sigma yz is equal to C2z. This has been derived from multiplication table of C2V point group. Here, the product of two reflection operations is a proper rotation symmetry operation. Let us see another example. Sigma A multiplied by sigma B is equal to C3. This has been taken from the multiplication table of C3V point group. Here also, the product of two reflection operations is a proper rotation symmetry operation. Rule number 2. The product of two reflections in planes meeting at an angle theta is a rotation operation by 2 theta about an axis formed by the line of intersection of the planes as illustrated below. Let us see it again. The product of two reflections, product of two reflection operations in planes meeting at an angle theta is nothing but a proper rotation symmetry operation by 2 theta about an axis formed by the line of intersection of these two planes. Let us illustrate it with an example. It is H2O molecule which has two planes of symmetry, sigma xz and sigma yz. Sigma xz is the molecular plane and sigma yz plane bisects the angle between H dash OH. Let us apply sigma yz operation. It means H2O molecule is reflected through this plane. As a result, the image of this black colored H atom will be formed here, and the H dash, blue colored H dash atom will move to this position and we get orientation number 2. Let us now apply sigma xz operation on this H2O molecule. If H2O molecule is reflected through the molecular plane, there will be no change in the orientation and we get orientation number 3. Here sigma yz and sigma xz operations are applied successively on H2O molecule. The orientation 1 can be transformed into orientation 3 directly by C2Z operation. This operation is carried out about this line, about this axis, which is formed by the intersection of these two planes. The product of reflections of a molecule through planes meeting at an angle theta is equal to the rotation of molecule about an axis formed by the intersection of these two planes by 2 theta. C2 operation means rotation by 180 degree. These two planes meet at 90 degree and the product of these reflection operations is equal to the rotation of molecule about an axis formed by the intersection of these two planes by 2 theta. Here the angle is 90 and hence the rotation is carried out by 180 degree. It means sigma xz into sigma yz is equal to C2Z operation. Here the symmetry operation sigma yz written on the right hand side is carried out first, followed by the symmetry operation sigma xz written on the left hand side. Rule number 3. When there is a rotation operation Cn and a reflection in a plane containing the axis, if a reflection operation Cn can be carried out on a molecule and there is possible plane of symmetry containing that axis, there must be altogether n such reflections in a set of n planes separated by an angle 2 pi by 2n intersecting along the Cn axis. It means if a molecule contains Cn axis of symmetry and a plane of symmetry containing that axis, there will be altogether n planes of symmetry intersecting along Cn axis at an angle 2 pi by 2n. Let us see it again. If a molecule contains Cn axis of symmetry and one plane of symmetry containing that axis, there will be altogether n planes of symmetry containing that axis and intersecting one another at that axis at an angle of 2 pi by 2n. Let us illustrate it taking example of H2O molecule which contains C2 and sigma xz, which is the molecular plane. It is plane of symmetry. Then sigma xz multiplied by C2z is equal to sigma yz. If H2O molecule contains C2 axis of symmetry and one plane of symmetry, there will be another plane of symmetry and these two planes of symmetry intersect each other along C2 axis at an angle of 2 pi by 2n. That is, which has been illustrated on the next slide. Diagrammatic representation of the previous discussion. It is H2O molecule. It has C2 axis and two planes of symmetry, sigma xz and sigma yz, which intersect each other along C2 axis at an angle of 90 degree. It is obvious that H2O molecule contains C2 and two planes of symmetry passing through this axis, which intersect one another at 2 pi by 2n. Here 2, this is the value of pi and this is the value of n. The value of n is 2. That is 90 degree. These two planes intersect along this axis at an angle of 90 degree, 2 pi by 2n, that is 90 degree. It contains C2 axis and two sigma z intersecting along C2 axis at an angle of 90 degree. Another diagrammatic illustration. Let us consider example of NH3 molecule which contains C3 and 1 sigma A. Then sigma A multiplied by C3 will be another sigma B. This is one reflection operation, and sigma A multiplied by C3 produces another reflection operation, and sigma B multiplied by C3 produces sigma C. NH3 molecule contains one C3 and one plane of symmetry containing this axis. Then NH3 contains overall three planes of symmetry, sigma A, sigma B and sigma C. These are three planes of symmetry, sigma A, sigma B and sigma C, and these planes intersect along the C3 axis at an angle of 60 degree. It is obvious that NH3 molecule contains C3 and three planes of symmetry passing through this axis, which intersect one another at an angle of 2 pi by 2n. Here the value of n is 3 and the net result is 60 degree. NH3 molecule contains one C3 axis of symmetry and three vertical planes of symmetry containing this axis, and these planes of symmetry intersect one another along this C3 axis at an angle of 60 degree. Rule number 4. The product of two C2 operations about axes which intersect at an angle theta is a rotation by 2 theta about an axis perpendicular to the plane containing these two axes. The product of two C2 operations about axes which intersect each other at an angle theta is equal to rotation by 2 theta about an axis perpendicular to the plane containing these two axes. In other words, if a molecule contains two C2 perpendicular to each other, if this angle is 90 degree, there must be another C2 perpendicular to both of them. If two C2 are perpendicular to each other, that is the angle is theta, then the product of these rotation operations will be equal to another rotation operation about an axis perpendicular to the plane containing these two axes by an angle 2 theta. It can be represented diagrammatically as follows. Let a point with Cartesian coordinates x, y, z If C2 by operation is carried out on the molecule, there will be no change in y-axis. If the molecule is rotated by 180 degree about y-axis, there will be no change in y, while the coordinates x and z will have reverse sign. X will move to minus x and z will move to minus z. If thereafter be applied C2x of operation, there will be no change in x-axis, while y and z will have opposite signs. Y will move to minus y, while minus z will move to plus z. The net result of these two rotation operations is equal to rotation of molecule about z-axis by 180 degree. There will be no change in z, while x and y will move to opposite directions. It means C2x multiplied by C2y is equal to C2z. Here the symmetry operation C2y written on the right hand side is carried out first, followed by C2x, and their net result is equal to C2z operation. C2z operation is nothing but the rotation of molecule about z axis, which is perpendicular to xy plane by 180 degree. These two planes meet one another at an angle 90 degree, and the result of these two proper rotation symmetry operations is equal to another proper rotation symmetry operation about an axis perpendicular to this plane by an angle 2 theta, that is 180 degree here. C2x and C2y symmetry operations commute with each other. Now we apply first of all C2x operation, then x will have the same sign while y and z will have opposite sign. Now let us apply C2y operation. Y will have the same sign while x and y will have opposite sign. The net result of these two rotation operations can be carried out by rotating the molecule about z-axis by 180 degree. The z will have the same sign while x and b will have reversed sign. It means C2y multiplied by C2x is equal to C2z, and we have already seen that C2x multiplied by C2y is also C2z. It means C2x and C2y symmetry operations commute with each other. And finally, rule number 5. The following pairs of symmetry operations always commute with each other. Two rotation operations about the same axis always commute with each other. Reflections through planes perpendicular to each other. For example, in H2O molecule, reflections through xz and yz plane which meet one another at 90 degree commute with each other. Sigma xz and sigma yz symmetry operations commute with each other, while in NH3 molecule the planes of symmetry meet at 60 degree, and hence sigma a, sigma b and sigma c don't commute with each other. Inversion operation always commutes with any other symmetry operation. Two C2 operations about perpendicular axis commute with each other. For example, we have seen earlier that C2x and C2y operations about axis meeting at 90 degree commute with each other, and finally Cn and sigma h, where Cn is the vertical axis, always commute with each other. These are the general rules for the multiplication of symmetry operations as discussed in the earlier videos for multiplication table of C2V and C3V point group. Thank you for watching the video with patience. Please like and share the video. If you have not subscribed my channel yet, please subscribe it so that you may get information regarding my new videos in time. Thank you again.